So I'm really excited to be here, share some details of our experience growing Strava and our infrastructure on AWS. But first, let me just spend a little bit of time introducing myself. My name is Jacob Stultz. I manage the infrastructure team. So the infrastructure team at Strava more broadly is responsible for our core server-side systems that support our application. So this is mainly sort of everything necessary to run our application in production. I've been here for just over 5 years, the infrastructure team throughout that time. And before I came to Strava, I had a background in kernel and database development. This photo is probably the simultaneous best and worst photo of me ever. It's felt like, sort of typical people put like photos of themselves in extreme situations, which I think that qualifies. That sort of accurately reflects my state of mind for the past year or so since I had my twins. So let me introduce Strava. So Strava is a social network for athletes. But I want to clarify that we use the term athletes a little more broadly than some may sort of normally interpret it as. Strava isn't just intended for elite and professional athletes like Kilian Jornet climbing Everest, though we do have plenty of elite and professional athletes as well. It's more broadly just for people who sweat. And our goal is really to connect and inspire those people in their active endeavors. Athletes upload activities to us, runs, rides, etc., via either our mobile app, which provides a record experience, or GPS devices, smartwatches, Garmin cycling computers, etc. And so they can then view and track their activity over time, compare it with others' performance or their own performance over time, share experiences, add photos, that sort of thing, as well as discover new ways to be active through clubs, routes, etc. Historically, Strava was sort of really originally intended as an experience for cyclists. But these days, we actually support more than 35 different activity types. So we have about 170 employees over a few continents. As mentioned, about 35 million members. And notably, Sean mentioned that we're pretty much global, but not just like in terms of overall reach. It's really international in that over 82% of those users are outside the United States. And collectively, they've uploaded well over 1 billion activities in the past 9 years or so. So a little bit of background around Strava's architecture and some of the history there and how we scaled. So we started in 2009, and at the time, it was before I joined, but we've really sort of optimized for building quickly, and we settled on Ruby on Rails and MySQL, which I think was a pretty reasonable trade-off at the time. But then we grew, and that infrastructure began to struggle. I'm going to highlight two particular areas that we had the sort of challenges in. So one is scaling our data storage and retrieval systems, and the other is scaling our application logic. And both of those really tie in more to tie into the more in-depth discussion that you'll hear from Jeff. So first, on the data storage side, a single MySQL instance that we had originally was clearly not really going to cut it forever. We did a number of things over time. So the first thing was we started simply. So we just spun up more databases, and we partitioned those logically by table. So if we had particularly large tables or groups of tables with really high read or write load, we would sort of move them off into their own databases that outgrew the original database to isolate that and allow us to scale horizontally that way. The next step that we took over time was to really improve our read scaling capacity and our high availability story with a clustered database system. So we did research on sort of several options a couple of years ago, and we eventually settled on Aurora, which I gather from the Database Week agenda over there, you're probably all familiar with at this point. And then finally, another really big theme was looking at certain really heavy and expensive read patterns and pre-materializing the results of those reads as denormalized data sets. And primarily we use Cassandra for that. And secondly, on the scaling of the application logic side, we have a pretty rich feature set and some member actions, notably activity upload, that really trigger a lot of expensive downstream actions. Performing all of them in process in our Rails application was clearly untenable, not just from a performance standpoint, but also just in terms of application complexity and all that. So we ended up building out a lot more robust event-based background processing systems. So sort of a final note here, one of the things I really want to highlight is that I think the impact that individual engineers at Strava have. We have a lot of, again, rich feature set, a lot of structured data, and a lot of really interesting challenges on the boundary between product and infrastructure. The scale, breadth, and reach of our product on a per engineer basis, I think, is really high. For instance, on the infrastructure team, we've got this very large user base, and I only manage 5 people. And so we're just the 6 of us are basically responsible for all of that, and it's a really interesting challenge a lot of the time. And that potential to have impact that broadly is really the main reason I'm still at Strava 5 years after starting and still pretty happy. But that's it from me. So now I think Jeff will get into some of the real content.
So I'm going to talk to you about what a segment leaderboard is, and then talk about how we used to host them with previous architectures. And then kind of a love-hate-love relationship with Redis, where we used it initially early on, it worked great, and then we kind of had scaling challenges with it, and then how we basically then used it as use it in a new way to kind of help scale our segment leaderboard system. So a little bit about me. I'm a senior platform engineer at Strava. I've been at Strava for 3 years, but other than that, I've been working in technology, primarily at web technology companies and startups for about 10 years, usually on web tech or in distributed systems. I like being outside, bikes and dogs. I don't have twins, but we did go backpacking in Glacier a couple of years ago, so this picture is me being outside. Talk about segment leaderboards, which are basically a segment, which has been discussed before, and also a leaderboard. Segments are, within the Strava product, are user-created sections of the Earth. Usually they're a road or a trail, but I'll explain how they cannot be sometimes. They're specific to an activity type, so there may be a cycling segment, like you have a climb, for example, that is specific to bike riding. There's also running segments, which may be the same section of road, but are a different activity type, so runners compete with runners, cyclists compete with cyclists. We currently have millions of segments around the world, and more are being created every day. We also have virtual segments. So this is a software product that we don't own or maintain as a separate company called Zwift. And they have virtual rides. So you'll see on the map, there's this red line that starts in the ocean and continues up a mountain and around. But that's actually, the activity is mapped to a real portion of Earth, but you ride your bike on a trainer in your apartment attached to a computer. And so this particular segment has like a lot of activities on it because basically anybody who's training in the winter for cycling or wants to ride at home, we ride down a virtual segment. So this one has 1 million attempts and about 167,000 people that are on the leaderboard. So then leaderboards, when you upload an activity to Strava with a GPS feed, anytime your activity traverses a segment, we call that a segment effort. So for example, if you go to Golden Gate Park and you ride around the polo fields, which is a cycling track, that polo field lap is one segment effort. You may have multiple segment efforts on the same segment per activity, or you may have one, it just depends. Your fastest segment effort for you is ranked on a segment leaderboard. So if you did your climb and your fastest time was 10 minutes, even though you may have like 11-minute time or 12-minute time, we take your fastest 10-minute time and that's your ranking on the leaderboard. A couple initial challenges with leaderboards are complexity and scale. So in terms of the product, we offer a lot of different combinations of leaderboards. So there's 18 static kind of base leaderboards. Those are usually for age groups or weight classes. There's 2 what we call dynamic leaderboards. So those are things like a leaderboard of people that you're currently following right now, or people that are a member of a club. You can see leaderboards just of those athletes. And then from those 18 base static or 2 dynamic leaderboards, we offer sort of 8 combinations of filters, or 8 filters rather, that are either sort of temporal, so like this month, this year, or gender-based, so everybody, or just men or just women. What that ends up being is about 300 different permutations of leaderboards. We denormalize, so we keep sort of in a database the 50 most popular denormalizations. And then for everything else, we kind of have one of 2 tactics. We either query our canonical effort storage, which is in MySQL, or we will scan the entire leaderboard, which is kind of sad, and then filter as we need to. These are just some numbers for scale. We see a lot of activities a week, about 15 million. Our traffic is very seasonal, diurnal, and sort of is spiky. So at a low time period, you'll see like 250 efforts a second. At really fast peak periods, like on a weekend, Sunday morning, for example, we'll see like 2,500 efforts a second. In gross, we do about 500 million efforts a week, which is a lot. And then large segments, kind of like that Zwift one I showed earlier, the virtual ride, they have millions of attempts on them and usually like hundreds of thousands of athletes. So we have pretty big segments. And then in terms of reads to the leaderboard system, depending upon traffic, again, it's somewhere between 1 to 5,000 requests a second from users. And then internal systems also use segment leaderboards to do some other features. Those have 700 to 2,000 requests a second. So if you, as I mentioned before, it's like a highly variable workload. Like it's like 10x difference between low traffic and high traffic. So it's kind of how segment leaderboards work. We'll talk about a very short history of the architecture we've had. So Strava launched in 2009, and then we used to do leaderboards back in 2010, right afterwards. We had them primarily done with SQL. directly in our Rails application. So we had a table that had all of the efforts. We would basically write a SQL query that says, sort them this way with this filter, and we'll give you your leaderboard back. That worked really well early on, but as we scaled, it scaled really poorly. Our data set grew, so we had more efforts to query. And then we also wanted to add more filtered leaderboards. Early on, we only did like one leaderboard per segment. We wanted to add more filtered options. So there's some work that was done that ended in 2012 to actually launch leaderboards on Redis. So what this means is that we still controlled effort addition or effort create and delete within the Rails application, but we use Redis as a data store as opposed to MySQL. This worked really well because Redis has a sorted set data structure, and leaderboards are a sorted data structure. So ranking queries are really easy and cheap. We were so excited about it, wrote a blog post back in September. You can look this up if you want, but the main reason I brought this up is we, in that blog post, noted that we were using one Redis server to host all of our leaderboards, and it was under 16 gigs of RAM. That was in 2012, so fast forward to 2016. At that point in time, I've had one engineer working on leaderboards basically full time. They were either fighting fires, fixing the current system, or they were working on the new kind of next iteration. We no longer had a 16 gigabyte Redis node. We had a 60 node Redis cluster with 1.8 terabytes of available memory. Also, that cluster was then fronted not by a Rails application, but by a leaderboard service that was written in Scala. And that was running between weekday, weekends, about 40 to 60 EC2 nodes. We added a lot more leaderboard filters. I talked about this before, age and weight. And then as we kind of grew and got more traffic, we started to have many unsustainable operational problems. So the few highlights from those problems were basically the concurrency model of the old system was really hard to kind of reason about and debug and diagnose. We saw lots of data inconsistencies where we'd have like negative leaderboard counts or people will be missing, things like that. A few incidents were caused by leaderboards. Some caused site outages, which are bad, and then also some caused upload outages, which was really bad for us. So kind of operationally really challenging. In 2016, we decided let's spend some time diagnosing these problems and kind of figure out what to do. I spent probably a couple of months looking at the old system, understanding how it worked, what we wanted from leaderboards, and kind of identified a bunch of systemic issues. One of them, not entirely, but one of them I kind of decided we talked about was our use of Redis. And not that Redis is inherently bad, just kind of how we chose to grow and use it ended up causing some problems. One is that Redis requires your working set to be in memory. So unlike MySQL or Cassandra or other databases where disk is the primary storage, Redis uses memory, which is great because it makes it really, really fast. However, memory is very, very expensive to scale. We were spending like a non-trivial amount of money hosting leaderboards, and looking at upgrading to the next level was like a substantial chunk of more money. Because we were sort of memory constrained, we actually had to ration what data to store. So we limited our denormalization of leaderboards just to two different kinds, the overall and then the female leaderboard. And then all other data structure, or all other leaderboards were serviced by one other data structure. So this meant that for a lot of updates to leaderboards, or we would have a lot of contention because there will only be like a handful of segments per leaderboard that we had to actually update. So a lot of people are fighting to write to that data structure. It's also wasteful to keep everything in memory because while we had millions of segments and like tens of millions of leaderboards, only a small portion of them are actually really read from at any one time. So we're paying money to host leaderboards in memory, and no one's really reading from them. So that's kind of another thing that was wasteful in our book. The second issue with Redis is sort of its lack of parallelism. Redis is single-threaded. What that means is basically it can only process one command at a time. It's really, really, really fast at processing commands, but it's only one at a time. This is somewhat mitigated as we did. If you shard your data set, you can have multiple Redis instances, but you're still sort of limited by this one thread operating on all commands that are sent. That was bad, but additionally, we had like a very command-intensive design. So we sharded by segment ID, which created hotspots. So if like for Ride London, it was talked about earlier, if there's a London segment that's really big, everyone's trying to add their upload to it. There's a lot of contention on trying to update that leaderboard in memory. And then because we were limited in our denormalization options, because of memory constraints, we had a lot of full leaderboard scans to produce filtered leaderboards. And then the old system used distributed locks for synchronization, which because it was using lock, it had a lot of commands for asking for a lock, waiting for a lock to be acquired, or releasing a lock, and there's a lot of chatter to kind of worry about. And the final Redis issue that we had was kind of a very poor ops story. So Redis is not easy to recover from a node failure. You can fail over to a replica, That's great, but you have to run both a primary Redis and now a replica as standby. And even if you have a replica, there's still some downtime when you promote it to a primary. You can't serve traffic, which is bad in our situation because we're trying to process leaderboard writes for uploads and also leaderboard reads as well. And in our case, we also had 60 Redis nodes, which is quite a lot of surface area for failures to occur. Additionally, the recovery mechanism for Redis to promote a replica is this thing called Redis Sentinel, which is not really proven in production. There's a quote there from a blog post, which I know you can't click on, but if you look up Jepsen Redis Redux, you can read it. Redis Sentinel has some issues with data loss or corruption when there was sort of significant errors, and so that was a little scary for us to kind of worry about for our canonical storage. And then finally, Redis is a little tedious to rebalance, so if let's say you have like a 60 node cluster and you want to go to an 80 node cluster, you have to sort of manually move data around and think about that. There are tools now in Redis that make that a little bit easier, but we were not using them at the time. And instead, there's a lot of manual work that people had to do to kind of move shards of data around to kind of rebalance as you wanted to grow the cluster. So we did all this work analyzing our problem. We wanted to work on a more scalable solution to leaderboards. And so in late 2017, we actually shipped it. There's a blog post series about this, which I wrote, which you can read. It talks about sort of the new changes to the new system and some background. There's a lot of things that got upgraded. Most of them are outside the scope of this talk. But the two things to take away were that we switched from Redis to Cassandra for our canonical leaderboard storage. And then we changed the leaderboard service from an RPC system to a stream processing system. This is sort of a very rough diagram of the architecture. Previously, all updates to the data store were done by a Rails application making a request on upload and getting a response back. Instead, with the new system, what happens is that Rails will log an event that an upload has occurred, and then there's a worker that consumes that at its own pace, and then updates leaderboard storage. And then leaderboard storage is then read from on the bottom of this graph to show where API responses come back. That said, Cassandra is not a panacea. So it's great. Cassandra is great, but it has sort of a limited data model. It's really good for returning ordered rows, in our case, leaderboard entries. But for direct access, like give me this rank of this user who is in this leaderboard, it's actually kind of expensive and necessitates effectively a full leaderboard scan. In testing a new cluster with our traffic, we actually had some the cluster was overwhelmed in our tests, and so we trying to figure out what we're going to do about this problem. And we've used Redis before because it has a sorted set data structure, which is very natural to leaderboards. Maybe we can add that back as a cache. And so that's what we did basically, is we reintroduced Redis as a cache. And so we noticed that with our request pattern, only a small portion of leaderboards are actually read from, as I mentioned earlier. These leaderboards that are read from tend to be the largest leaderboards, which are also the most expensive ones for Cassandra to serve. So if we cache them, that would be great. And then Redis then can be used as a ephemeral cache. So it can hold a portion of the full data set, only the most requested leaderboards. And if we lose our cache node, that's actually totally okay, because you can read from the origin, which from Cassandra if you need to. So as I mentioned before, Redis is using Redis as a cache kind of addresses many of our original complaints. We're no longer constrained by memory. We still have to keep everything in memory, but we can create a data structure in memory that's much richer and faster to query from, and only keep a portion of leaderboards in that structure. So much greater command speed. As I mentioned, good op story. If a node fails, we can replace it with an empty one and it'll get filled back up. With cache misses, that's totally okay. And then you have this option during a failover to read from Cassandra if you'd like. We looked at a bunch of Redis solutions for doing clustered Redis and eventually settled on Elasticache from AWS. So we run a Redis 3.something cluster, and AWS is great because it handles ops, health checking, failover. We kind of just let it run and it happily and it does its thing. So going back to this diagram, this is basically what we added. So when an update is made to Cassandra, say you got a new PR on the climb, that logs an event that occurred, and then there's a worker consuming those events and keeping the cache up to date. And then those cache responses are then available to our API, so it can choose to read from the cache if there's a cache leaderboard available. If not, it can then read from Cassandra. Okay, I want to talk about updating the cache with changes, which is a little bit tricky and also interesting, I think. If you think about leaderboards as a cached data structure, anytime anybody gets a new PR on a segment, let's say go for a ride on your climb and you get a new best time, you were ranked 1,666, you're now ranked 500th. Your row in the cache leaderboard is now invalid, and then the rankings have shifted, so everybody who you've now outpaced is now at a lower ranking and their ranking is wrong. So there's near constant invalidation for leaderboards. So we need to be conscious of how to cache things or how to update things kind of quickly and effectively with minimal data staleness. So the way that cached leaderboards get populated is one of two ways. One is that if there's a cache miss from the API, there's an asynchronous process that fetches the whole leaderboard and puts it in cache. That's a populate. And then anytime Cassandra has a change, we then do an update to an equivalent cache leaderboard entry. I'll talk more about how that update works in a second, but that was sort of the two modes that leaderboard updates happen. And then we use an LRU, which is last recently used eviction strategy for leaderboards to make sure that we only keep the most recently read from the most popular leaderboards in cache. During these updates, we're actually writing many separate Redis commands and updating many different data structures. We do that basically for performance reasons to make sure that we have a way to handle most leaderboard queries effectively and quickly. However, between those commands, if you do a read, you could see incorrect data, you could see corrupt data or partial data, or if we're crashing in the middle of doing a write, we could corrupt the data. So we really want to run multiple Redis commands atomically, but thankfully Redis has a solution for this, which is to use Lua. So Lua is a weird little scripting language that Redis embeds in itself as an embeddable engine, and then you can write Lua scripts and have them run by Redis. Redis scripts have access to all the Redis commands. You can write them as needed, and then they run atomically, which is really great. Good for our use case. So we implemented sort of 5 synthetic commands in Redis to update leaderboards, and they sort of manage that for us. There, you say, hey, leaderboard, add this athlete with this entry to your leaderboard, and it updates the necessary data structures in one go to keep everything in sync, and then returns the result when it's done. This is a graph of the hit rate to the cache for various leaderboard commands. So green means there's a cache hit, which went to Redis, and then red means there's a cache miss, which went to Cassandra. Basically, 70–75% of all requests for most leaderboard commands are cached. There's one, the bottom left one is only about 40–35%. That one's not called as often, so it's not as much of a concern for us. And then this graph is a graph of total reads with Redis versus Cassandra. So Redis is blue, and then Cassandra is green. So you can see that for any given time period, the amount of Redis reads is generally larger than the amount of Cassandra reads, which shows that our cache is working. We're getting more reads to Redis than we are to Cassandra. That's a good thing for Cassandra. In conclusion, so I talked about our historic scaling challenges, kind of how Redis was good initially, but then kind of as we grew, it became a really poor choice for a canonical store, like a large growing data set that needs high availability. Other data stores like Cassandra, in our case, can meet those needs well. However, Redis does have some really great use cases, and one of them is an ephemeral cache. So that's what we did. We kind of had a very targeted, specific use case for Redis, and we used Redis to do what it does really well. And that allows you to, with Redis and then Lua scripting, you can kind of design optimal data structures that meets your needs, meets your use cases really well, and provides really good, very flexible cache. And that is it.